this alternating quantity by a vector. So again, kept reference axis as it is. Draw one circle and radius of the circle should be equal to amplitude of alternating quantity. Okay, in this diagram we are assumed that the magnitude of both the quantities are same, but both are having some phase difference. So for this first quantity, this is our origin denoted by O. For this first quantity, the vector is OA. It will indicate that your quantity having 0 value at 0 angle. Now for this second quantity, if you are extend this quantity like this, then the 0 value of the second quantity at this particular point. Take the projection of this point on the circle and draw one vector which is B. Angle between these two is phi, which is equal to phi over here. So this is the representation of two quantity by a vector. Now if you are change the position of vector from 0 degree to 90 degree, then what happen? If you are rotate this vector to 90 degree, then it is like this. Here it is OA and somewhere here it is OB. Again, angle between these two is same because we are assuming that the frequency of both the quantities are same. Again, if you are rotating at this point, here it is OA and somewhere here it is OB. Again, angle is equal to phi. Same way for this particular point, here it is OA, here it is OB, angle is phi, and finally you come to the initial position and angle remains same. Same thing is drawn in this diagram. In this particular point, phase difference between these two is phi, which is equal to 30 degree, and at any point if you are found the phase difference of these two, so it is constant at 30 degree. So throughout the cycle, both the quantity having same phase difference, and throughout the circle for both the vector having same phase difference. Here it is phi, phi, phi and phi. So the phase difference between these two vector is constant throughout the rotation. Same way for alternating quantity, phase differences remains constant throughout the cycle. So you can represent two vector quantity having same frequency by a vector representation. Now addition of two vectors. So we are assuming that we are having two vector, vector v1 and vector v2. It is like this. This is our first vector v1 and second vector v2. As shown in figure, v1 is considered as a reference axis. It is on a reference axis, means angle from the reference axis is 0, and v2 having some angle from the reference axis. So resultant of this two vector you can found by a parallelogram method, which is shown in a figure. So this is the figure. This is our v1 vector, vector v1, which is on a reference axis, means angle of v1 is equal to 0. This is our vector v2, angle from the reference axis it is theta. Draw one line which is connected v1, initial point of v1 and final point of v2. It will give you the resultant value, which is denoted by r. So this method is known to you. Same method you can use to find a resultant value for two alternating current or two alternating voltage also. So resultant voltage can be found by this equation OB, which is resultant vector, is equal to OA plus OB. Now OA plus OB is not an algebraic sum, it is a vector sum. So you have to consider the effect of vector also. So resultant vector R is equal to V1 plus V2. So using this formula you can find the resultant value. Same method you can use to find a resultant for a alternating quantity. So this is the vector addition using resolution method. So in this method we are assuming that we are having two alternating quantity. First is R1, which is equal to Im1 sin omega t, means the phase angle of R1 is equal to 0, and second R2, which is equal to Im2 sin omega t minus phi. So which is shown by OB. Here OA is equal to R1 and OB is equal to R2. OA having a 0 phase difference, so OA is on the x-axis and OB having a phase difference of phi, and here it is omega t minus phi. It will indicate that OB is lagging behind the OA, so OB is drawn like this. This is our OB vector, angle is phi, but here it is minus phi, so we have to shown over here. Now as we are discussed earlier, every quantity having two component, one is the x component, another is the y component. Same way for Im2 also having two components, one on the x-axis, another on the y-axis. So Im2 is distributed like this. This is the x component of Im2 and this is the y component of Im2. So Im2 cos phi and Im2 sin phi. Now if you have to make the addition of vector, then direction of component of Im2 on the x direction and direction of Im1 is same. So this is our Im1, which is represented by OA. Now AD is the x component of Im2. So this OD will indicate the vector addition of OA plus AD, and this DC will indicate the y component of Im2. So this OD and C will show one triangle. So this OC is the resultant value of this triangle. So if you have to find the resultant, which is denoted by IR, so OC is equal to under root of OD square plus CD square. Now OD is nothing but the addition of OA plus AD, and CD is nothing but the y component of Im2. So using this equation you can find the resultant value of current. So IR magnitude is equal to OC, which is equal to OA plus OD plus CD square. Now OA is nothing but the Im1. Im1 lies on the x-axis, so the y component of the Im1 is 0. So always keep in mind, whenever the vector placed on the coordinate axis, then the other component will be 0. If your vector is placed on the y-axis, then the x component of the vector is equal to 0, and if it placed on a x-axis, then y component is 0, and if it placed on a y-axis, x component is 0. Now OA is equal to Im1 and AD is the x component of Im2, so it is equal to Im2 cos phi, and CD is equal to y component of Im2, which is equal to Im2 sin phi. So if you have solved this equation, you got the magnitude of resultant current. So this first bracket indicate the x component of current and second bracket indicate the y component of current. So you can rewrite this equation like this. IR magnitude is equal to under root of x component square plus y component square. Now this will give you the magnitude of resultant value. If you have to find the phase angle of the resultant current, then equation is like this: tan of alpha, alpha is the phase angle, which is equal to y component divided by x component. If you have to have a number of currents, suppose 3 current, then the total y component of all the 3 currents divided by total x component of all the 3 currents give you the value of tan alpha, and tan inverse of this give you the angle, which is phase angle of the resultant value. If alpha is positive, it will indicate that your resultant current is leading, and if alpha is negative, then it will indicate your resultant current is lagging. So your final equation for a resultant current is written like this: IR is equal to IR magnitude sine omega t plus or minus alpha. The value of alpha is depends upon the x component and y component of the current. It may be leading, it may be lagging, depends upon the magnitude of currents or behavior of circuit element. Now next is examples related with the vector representation. So find the magnitude and resultant of voltage for a given figure. One diagram is given to you, and from this diagram you have to find the magnitude as well as the resultant value of the voltage. So this is the diagram as shown in figure. This is vector V1, which is given, value is given 20 volt. This is vector V2, the value of V2 is 30 volt, and you have to find the resultant of these two. Angle between these two is also specified, it is 60. V1 is represented like this, V1 sin omega t plus phi, and V2 is represented like V2 sin omega t. So V2 is at the reference axis and V1 having some phase difference which is equal to 60 degree. You have to find the value of Vt. This blue vector is the total voltage, or you can this resultant voltage. You have to find the magnitude and phase angle of this Vt. So as we had discussed earlier, that you can find the resultant value of voltage or current using the resolution method. So voltage V2 of 30 volt in the reference direction along the horizontal 0 axis, then it has a horizontal component but vertical component is 0. As we had discussed earlier, if any vector is placed on the coordinate axis, then the other component will be equal to 0. Now horizontal component is equal to magnitude of the vector, which is 30, into cos of the given angle. Now angle for a reference axis is 0, so 30 cos 0, so value is 30 volts. Same way for vertical component, it is placed on a x-axis, so vertical component is 0, so it is 30 sin 0, so it will give you the 0 value. Now vertical component for V1, voltage V1, magnitude of it is 20 volts and leads voltage V2 by 60 degree. Then it has both the component, because it is not on the coordinate axis, it is between these two axes, so it has both the components, horizontal component as well as vertical component. Now horizontal component is equal to again magnitude into cos of the given angle, so it is 20 cos 60, so it is equal to 20 into 0.5, so it will give you the 10 volts. And second vertical component, which is equal to 20, angle is equal to 60 degree, so 20 into sin 60, so it will give you the 17.32 volts. So resultant voltage is found by adding together the horizontal and vertical components of both the currents. So this is the total. V horizontal means sum of real parts of V1 and V2, as we are find the horizontal component of V1 and horizontal component of V2, so it is 30 plus 10, so finally it is 40 volts. Same way addition of vertical components, so for first it is placed on a x-axis, so the vertical component is 0, and for second voltage it is 17.32, so our final answer is 17.32 volt. Now resultant voltage. So this is the equation for resultant voltage, under root of horizontal component square plus vertical component square. So value of horizontal component and vertical component is known to us. So Vt is equal to under root of horizontal component is 40, so 40 square plus 17.32 square. Your answer is equal to 43.6 volts. This is the phasor diagram for a resultant voltage. So as shown in figure, this blue vector will indicate the resultant voltage. This dotted line indicate the vertical component that we are found, which is 17.32, and this horizontal line indicate the horizontal component, and the value of horizontal component is 40 volts. So this is the vector representation, and the magnitude of this particular resultant voltage is 43.6 volt. So this is the magnitude of the resultant vector, this is the vertical component, and this is the horizontal component of the resultant voltage. So using this equation you can find the resultant of any voltage or current for a number of voltages given to you or number of currents given to you. This is another example. Two alternating current are given to you. First I1, which is equal to 7 sin omega t, and I2, which is equal to 10 sin omega t plus pi by 3, are fed into a common conductor find magnitude and phase angle of resultant. So two currents are given to you. First is I1 is equal to 7 sin omega t and second is equal to 10 sin omega t plus pi by 3. So using same method you can find the resultant of this two current. So this diagram will indicate the vector representation of alternating quantity. As we had discussed earlier, first current is 7 sin omega t. It will indicate that the magnitude of current is 7 and phase angle is 0. So it is represented by OA. This is our OA, which is placed on a x-axis. So phase angle is 0 and magnitude of this vector is 7. Now this is OB. This is our second current I2. The magnitude of current is 10. So the magnitude of OB is equal to 10. Sin omega t plus pi by 3 means it will indicate the phase angle between these two is pi by 3. So this angle is equal to pi by 3. Here it is positive. So here it is in a first quadrant. If it is negative, then it comes in a fourth quadrant. So this is our vector OA. This is our vector OB. Now as we are discussing earlier example, same way you have to find the x component and y component of both the current and then find the resultant of the current. Now we have to find the horizontal component and vertical component of the given current. So first of all we are finding the horizontal component. So first current is I1 sin omega t, magnitude is 7. So x component is equal to OA plus OB cos 60. So magnitude of OA is equal to 7, magnitude of OB is equal to 10. So here it is 7 plus 10 plus cos 60. Your answer is equal to 12. This is the x component of both the current. Now y component is equal to OB sin 60. Now y component of OA is equal to 0 because it is placed on a x-axis. So magnitude of OB is equal to 10. So here it is 10 sin 60 and your answer is equal to 8.66. Now x component and y component of both the currents are known to us. So we are finding the magnitude of the resultant, which is equal to under root of x component square plus y component square. So which is equal to under root of 12 square plus 8.66 square. And your answer is equal to 14.79. So this is the magnitude of the resultant voltage. Now we are finding the phase angle of the resultant. So the equation is known to you. Phi is equal to tan inverse of y component by x component. Y